So Qingyu is our speaker who worked with Michelle, Florent, and Rob for her PhD. She started her PhD in 2015. And at the same year, she got the master degree in solid earth sciences from the University of Joseph Furiel. Now the university was changed, the name changed to be the Grenoble, but it is the same university. So, so during her PhD, Qingyu and her group did the first largest scale monitoring and the first tilde-meter monitoring to investigate the subsurface structure change after the 2011 Tohoku earthquake. This year is her last year of the PhD, so she planned to find the postdoc position in US. So if anyone here is interested in her work, so he's very happy to talk with people and probably find a position here at EIL. So yeah. So now let's welcome Qingyu to talk about the ambient noise-based seismic monitoring of the evolution of mechanical properties of the crust beneath Japan. So yeah, thank you, Qingyu.
Thank you, Chen. Did it work? Thank you. Welcome to my talk. Today I'll be talking about the ambient noise-based monitoring throughout Japan. This work is done with all my supervisors and some Japanese colleagues in Tokyo University, Tohoku University, and from NID. The topic of this talk is to monitor the mechanical properties of the crust beneath Japan. We aim to give a comprehensive application of noise-based monitoring throughout Japan in both long-time and seasonal scales. As we know that the Earth is constantly deforming, but the mechanism behind this is still not fully understood yet. There's some studies from noise-based monitoring to follow the deformation of the crust, such as some earthquake-related deformation and some seasonal deformation. For example, the 2004 Parkfield earthquake that had been started by Hongieto in 2014, they showed an exponential post-seismic relaxation, which the authors contribute the deformation to co-seismic damage in shallow layers, and co-seismic static strain change, and post-seismic stress relaxation within the fault zone. Regarding the seasonal changes, the first observation of noise-based monitoring was by Schoenfelder et al. In 2008. The authors found the velocity changes in Indonesia at Merapi volcano that the velocity decreases every year, and then some very regular annual patterns. And they explain these seasonal patterns by modeled groundwater level. When the groundwater level increases, the velocity decreases. This probably because the groundwater level increase, the pore pressure increase, and the pore pressure will reduce the shear modulus, thus decrease the velocity. And after these studies, a bunch of similar studies regarding the earthquake-related deformation and seasonal deformation have been carried out in the following years. So, inspired by all these studies, we want to do an integrated application of noise monitoring in Japan. As we know, Japanese island located in a very active plate boundary zone, the four lithospheric plates converge on one another. Therefore, Japan experienced considerable seismic and volcanic activities. Under the impact of 1995 Kobe earthquake, Japan started to deploy the high sensitivity seismograph network throughout all Japan. And the seismometers were installed in downhole. The downhole settings can ensure a good data quality. In this study, we benefit from the dense HyNet network from 2008 to 2012 in the northeast part, and from 2011 to 2012 in southwest part. This time period covered the magnitude 9 2011 Tohoku earthquake, which is the most powerful earthquake that has ever been recorded in Japan. This figure shows the co-seismic slip distribution, jointly inverted from teleseismic local strong motion and the GPS data. And we see the co-seismic slip normally happened along the Japan Trench and spread onshore. This red point indicates the aftershocks within 1 week after the main shock. Tohoku earthquake-related both co- and post-seismic deformation have been widely discussed in geodetic field. The mechanism behind this is very diverse and intricate. So inspired by all this high-density network and previous studies, we decided to do the monitoring in Japan to better understand the deformation in different depths in the crust, to better understand the mechanism of the occurrence of earthquake. So the basic principle of noise-based monitoring is if we cross-correlate any two signals recorded in station A and B, it can reconstruct the waves generated from station A to B in the crucial part and from station B to A in a crucial part. They carry the information of the medium where the wave passed through. Once the medium undergoes the change, the velocities and the waveforms change too. And the monitoring is normally done using the coda waves, the later arrivals of the waveform. And using coda waves has some advantage that its scattered wave can help easy some shortcomings from non-homogeneously distribution of noise source. And also, with last time goes on, the phase shift between any two couples of course correlation accumulates. So it can help us to get a stable phase shift measurement. So now we move to our study. There are mainly two parts of this study in Japan. The first one is
Give the lights over there.
it doesn't matter. I will show it up later.
Animation to show
Animation, yes.
It's all writing there.
You will.
You will have it.
See?
Yeah. That's two different parts. The first part is some seasonal effect related velocity changes that happen mainly in the shallow layer. And the second part is Cancer's 2011 Tohoku earthquake. So in the first part, we use more than 700 stations throughout Japan. I will show you in this part some single station seasonal features, how it looks like at different locations, and do some regional analysis to identify the seasonal effect at different locations, and to crack this seasonal effect. And I will end up by some compared studies with some geodesic observations, like Grace measured gravity field or GPS vertical displacement. So in this study, we adopt the method doublet plus inversion by Wang et al. In 2014. It has been proved to be the most powerful method till now for monitoring. But yeah, of course, there are some new method ongoing. In this study, we use 3 components, thus the 9 component correlation within 30 kilometers. And the first study is measured within this frequency range, 0.15 to 0.9 hertz. In this frequency range, velocity changes essentially sample the changes with depth less than 8 kilometers in upper crust. And here I select 4 different stations to show you how the velocity changes look like in different locations. And then you see there are some quick velocity drops that coincident with different earthquakes. From north to south, they are separately Togashi-Oki earthquake, Iwade earthquake, Tohoku-Oki earthquake, Shizuoka earthquake. This earthquake-related velocity drops are normally followed by a long-term recovery. And besides this, there are some very strong regular annual patterns that have an order comparable to the earthquake-related velocity changes. And they are so different at different locations. This may imply that, and this annual pattern, we call it seasonal effect. And these different features at different locations may imply that for different regions, they are predominated by different physical postures. Here's a movie to show you how the seasonal effect look like throughout Japan. In this movie, we can see 2 big anomalies of velocity changes in eastern corner of Hokkaido and in Tohoku. The 2 are different. This one begins from a positive value and starts to be negative from April, and the Kyushu start to be negative from June. Both of them have a fluctuation with order 10 to minus 2%. The 2 anomalies may indicate some very different physical postures. And there's another figure to show the seasonal effect distribution. This is actually the cross-correlation map using annual signals over different years, and we take the average value to map the cross-correlation. We call it seasonality strength. So when the value is big, the seasonality strength is high. We see in both Hokkaido, in Kyushu, and along the western coast of Honshu, they show strong seasonality strength. So we decide to separate different regions to see the seasonal effect. And first, we start with the case in Kyushu, as Kyushu has a relatively simple environmental condition. There's almost no snow recording in winter, but they have strong precipitation in each summer. As I just showed the case, the first observation of seasonal effect, they compare the groundwater level with velocity changes. And we also compare the velocity changes to the precipitation-induced pore pressure changes. This pore pressure changes is calculated using all the meteorological data over more than 90 meteorological stations in Kyushu. And we see the shape of these pore pressure changes looks quite like the seasonal effect in Kyushu. So we assume a linear relationship between the changes of pore pressure and the changes of velocity. We get the real sensitive velocity changes, which cover very well to the mean measurement shown by the black curve. And in Kyushu, there is another feature we need to note, that the biggest velocity changes happened in the volcanic region. This confirms the conclusion by Wang et al. In 2014 that volcanic region has a higher susceptibility of velocity changes to dynamic stress perturbations. So in Kyushu, we identified the seasonal effect are mainly controlled by the precipitation-induced pore pressure changes.
So I have a question.
Yes.
So what is the black and red line in the DB overview?
Black and
the lower one. Yeah, what
Yeah.
is the gray line and the black and red line?
the gray are the measurements from more than 70 stations, seismic stations.
The average.
Yes, black is the average over all these gray lines.
And the red line is?
The red line is the synthetic from the pore pressure changes.
Can you mention the scale on the pore pressure changes? I can't.
It's Pascal to 200, but
Pascals.
yes, but you should note that it's an averaged pore pressure changes over different depths. It's quite dependent on the depths that we use to calculate the pore pressure. If we concentrate in shallow layers, it's quite high. If we go more deeper, it's getting smaller. So the value, the absolute value is kind of tricky. But
How deep do you go? How deep is your,
yes,
when you do that?
as
average?
this measurement is in the frequency range 0.015 to 0.9 hertz, so the velocity changes essentially happened within 8 kilometers. So we calculate the mean pore pressure changes within 8 kilometers. So it's getting smaller when going deeper. So this is the first big anomaly in Kyushu. And then we move to another anomaly in eastern corner of Hokkaido. In this region, the seasonal effects are very different from in Kyushu. They show a velocity increase in winter and a decrease in summer, which the increase is in the same time period as the snow accumulated season. And as in some geodesic studies, Haki et al. Show a lot of snow importance role in Japan. So here we consider the snow loading effect, and we assume a linear relationship between both changes of pore pressure and snow loading to the velocity changes, and we get this synthetic red curve, which covered very well to the black mean measurement over all these black triangle stations. And so in this region, we consider that the seasonal effects are from both pore pressure changes and snow loading effect.
What is the delay between those two?
Delayed
Between delta, the variation of velocity and precipitation, so the peaks are not at the same.
actually, if it's almost the same, the delayed effect is not too much if we calculate the pore pressure into very deep depths. If we just calculate the pore pressure in shallow depths, we see a big delay. But as we averaged, there's almost no delay. But the global shape remains the same. And so these are for the two big anomalies in eastern Hokkaido and in Kyushu. There's still some other stations along the coastal region in Hokkaido and in Kyushu, in Hokkaido and in Honshu that show strong seasonality strengths. Here I plot all stations with seasonality strength more than 0.6. You see clearly the seasonal effect for all stations. This seems quite uniform, except for some longitude 140 and 138. That's the Central Japanese Alps region and Kanto region. This shows slightly different seasonal effect. And all these stations show strong Tohoku earthquake-related velocity decrease at the same time. So we still decided to separate the central region and the very western region to analyze the seasonal effect. And for the central region, it's quite simple to find its origins in pore pressure changes. That, like in Kyushu, we use the precipitation-induced pore pressure changes, get the sensitive velocity changes, can easily explain all the seasonal signals. But for the rest region, either snow depths or pore pressure changes can easily explain the seasonal effect. So we considered still other two environmental factors. One is sea level changes. The other is atmospheric temperature changes. Both of them have some effect to geodetic observations. And the former one differ with almost 30 centimeters. 30 centimeters between summer and winter. It's not only an indicator of the environment, the surrounding environmental conditions, but also can generate some loading effect to the coastal stations. And the second one can generate some thermo-elastic effect with phase difference between the velocity and temperature changes. But in this study, we would like to build a linear relationship between using all these environmental factors, so we choose to yield the sea level changes as one reason for the seasonal effect. So we build a linear relationship based on these different meteorological and oceanographical observations. The pore pressure, snow depth, and the sea surface height is equivalent to sea level changes. And we build this linear relationship to calculate the sensitive velocity changes. And we build the sensitive velocity changes for single stations. And here I show 3 examples in different locations where the seasonal effects are quite strong. And we see the red sensitive velocity that recover very well to the narrowed seasonal effect. And for some stations, like in Kyushu, if there is no big event, after removing the red curve from the black measurement, we get the blue residue that is randomly noisy, and the minimum detectable velocity changes is down to 10 to minus 5. And some earthquake-related velocity decrease that previously hidden in the seasonal effect, and now it shows up. So this is good for us to follow a long-term tectonic-related deformation and some other advantage I will talk about later. And if we take a look at the quarterly seismic velocity changes, this is before correction, the first quarter from January to March, the third quarter from July to September. This is after correction. We see the 2 big anomalies almost disappear after correction. And the Iwate Miyagi earthquake-related velocity decrease remains there. It even becomes a little bit stronger after the correction. So it's good for us to follow long-term earthquake-related velocity changes. So after correction for all these stations, we do some statistical analysis of the velocity changes during the period without big earthquake. We call the period calm period. Here I show one example for station in eastern corner of Hokkaido. You see that before correction, the reason that we do this statistical analysis is that we want to get some probability density function for velocity changes during the calm period, and to quantitatively detect anomalies that related maybe to some earthquake or some eruption of volcanoes. And you see, before correction, velocity changes almost obey the normal distribution, and these contours plots are not perfectly straight. But after correction, it's almost perfectly normal distributed, and the line is very straight. It means it obeys very well the normal distribution. And actually, we did this statistical test for all stations, and all stations show the normal distribution for the calm period. So this can help us. This again confirms that our linear model can get rid of the deformation that related to some environmental factors that not related to the long-term tectonic deformation. And it gets rid of this non-random deformation, can help us to better sort out the velocity changes during the calm period, to to get a good probability density function. These are all seasonal effects about in Japan, and after this we compared velocity changes to some geodetic observations with both GRACE satellite measured gravity changes and GPS observations. First, this is a GRACE measured gravity field is represented by equivalent water level height in centimeters. I show 4 different locations that plot both velocity changes in black curve and 10 days EWH in blue. You see, for Hokkaido East, this shows positive correlation, which means that when the EWH is high, the velocity increase. Actually, in the snowy region, the EWH, the high value is mainly controlled by the snow depth. And for the region like in south, there's no snow, the high value is controlled by the strong precipitation in summer. So this positive correlation confirms the snow effect in this region. And in Kyushu, you'll see they are perfectly negatively correlated, which means that when the EWH is high, the velocity decreases. And here, the EWH high value is controlled by the precipitation in summer. And even for the long-term trend, they perfectly match. And for the rest 2 regions, the Central Alpes region and Kanto region, there's no big strong correlation between them. And for the rest, Western, Honshu, the 2 show strong negatively correlation, which means when EWH increase, the velocity decrease. But as we know, the GRACE data has a very poor spatial resolution with about 1 degree square. So in this region, they may be strongly affected by the Sea of Japan. We cannot get precise EWH for some point. But again, this comparison first confirms that the velocity changes are from some physical property related deformation in the crust. But GPS observation can provide a more higher spatial resolution comparison. Japan operates also GPS network called GeoNet with more than 1,000 stations. We use the data from 2008 to 2012, and we do the comparison with GPS vertical displacement to our velocity changes. I showed 3 different locations that they show very strong correlation with velocity changes. For example, in Kyushu, even for the long term, they match very well. When the GRACE vertical displacement move downwards, the seismic velocity decrease, which means for precipitation, velocity will decrease. However, the GRACE is more sensitive to the subsidence induced by the precipitation and go downwards. But for this region, they show negatively correlation, which probably due to both the poor pressure effect to GPS displacement and to velocity. In this region, the 2 show very well positive correlation when GPS increase and velocity increase too. And the shape and small change of them match pretty good. And so all these 3 different observations, the GPS measured gravity field and GRACE GRACE measured gravity field and GPS vertical displacement and velocity changes the three observations should complement each other to help to better understand the deformation in both long-term and seasonal scales. In order to understand better the mechanism for the occurrence of an earthquake. So this is the first part about the seasonal effect throughout Japan. In this part, I show the first time the largest scale monitoring till now, and we do some regional analysis to analyze different seasonal effects that could be related to pore pressure, snow depth, and sea surface height loading effect. And we build a linear model for correction based on different local meteorological and oceanographic observations. The comparison with geodetic observations show negative or positive correlation that means under the same environmental factors, the three measurements have very different response. So now I'll be moving to the second part about the 2011 Tohoku earthquake. I don't know if you have any question about the seasonal effect. You can just. I'm so pleased to answer any questions about this. And now I'm to move to this part. It's totally different to the first part. So yeah.
So the atmospheric loading,
Yes.
Atmospheric pressure doesn't.
Yes, we all.
It's too small.
Yeah, we always compare with the atmospheric pressure loading, but in both sides they have the same pressure. This is not the major reason to cause the different velocity changes in the western side and the eastern side. So we don't consider it's a major cause for the seasonal effect in that part.
Question?
Yes.
Since you mentioned the propagating effect for the cold wave is very complex,
Yes.
how did you get the velocity variation distribution?
Very good question. I will talk about this later in this part. So in this part, we use 171 tilt-meter station. This is the first time tilt-meter station used for noise-based monitoring. Tilt-meter station have two horizontal components. It measures the tilt of the Earth, and it could actually be regarded as broadband seismometer to do the monitoring. So it has the same density as high-net short period stations. So we have also very dense distribution of broadband seismometer to monitoring. Since it could be regarded as broadband seismometer, we can divide into different period ranges to get depth-dependent rheology. And this is a yes. And I will end up this part by towards 4D monitoring. In this study, we use also the doublet inversion method as the last part, and we use two horizontal components, so 4 component pairs. We calculate cross correlations within 100 kilometers. So this gives a basic spatial resolution that is not so good. And here I show you some single station velocity changes at different locations with different distance to the epicenter of Tohoku earthquake. Here you see both all 3 stations show some seismic drops that could be related to 3 different events. One is a 2008 divided earthquake, one is a Tohoku earthquake, and one is the biggest aftershock 1 month after the main shock of Tohoku earthquake. And you see for short period measurement, they have the biggest seismic drop. And when the period increase to 8 to 13 and 15 to 15, the co-seismic drop decrease, and there is kind of delayed seismic response regarding the longest period range. And with the interdistance increase, or the co-seismic amplitude decrease, especially the short period, it decreases much faster than the longer period. And the amplitude recover slowly for long period. All of these three different periods, velocity didn't recover to the initial level after the end of our observation. To analyze the post-seismic response in different period ranges, we first map the spatial post-seismic velocity changes during averaged over this time period, 6 months after the Tohoku earthquake. The three maps are separately in 1 to 7 seconds, 8 to 30, 15 to 50 seconds. We see that the co-seismic amplitude decrease when the period increase, and the most affected area shift from this region to northward. This different affected area distribution may imply that the different physical reasons for different period velocity changes. So first, for the short period in 1 to 7 seconds, we see the most affected area is centered here. It's not the most close region to the epicenter, and it could be related to some near-surface damage. So we compare this with PGV observation. This is root squared PGV over 3 different components. And we see the two spatial distribution are quite similar. This may imply that for the short period, it is actually some nonlinear behavior or the superficial unconsolidated shallow layers. But for long period, in 8 to 30 seconds, we see the velocity drops move northward, and the most affected area that is very similar to the co-seismic static strain change. This is modeled co-seismic static strain at depth of 20 kilometers. This is from the Freeze et al. In 2017. The layered structure considering both after sleep and after post-seismic viscoelastic effect. So this similarity suggests that for different steps, the existence of different behaviors and the first order conclusion could be that there are some specific changes at depth. This is a spatial comparison, and we also do some temporal evolution comparison for the most affected area. We choose 74 stations to do the monitoring, and we get this average velocity changes over this shaded area for 4 different period bands, from 1 second to up to 50 seconds. We see they show very different temporal evolutions. For short period, velocity decrease immediately when the earthquake happened, and it recovered quite quickly after the earthquake. However, for longer period, the co-seismic drop are smaller, and it's important to highlight delayed response for longer period. The green curve is not so obvious in this screen, and This may suggest a depth-dependent rheology with some non-elastic behavior that extended from lower crust to upper. And till now, we all discussed the velocity changes in different period ranges. We don't know exactly what the depths they are, so we first invert them into 5 layers depths up to 50 kilometers. First, we invert velocity changes based on the Rayleigh sensitivity kernels. This is a kernel in different period ranges, and we get the inversion result of velocity changes in 5 different layers to 50 kilometers. We see the amplitude decrease a lot with depth, and the delayed effect increase with depth too. The recovery seems to be a little faster in the deeper part, and the most strong velocity changes happen within 30 kilometers. Below 30 kilometers, the fluctuation and the velocity changes level are quite similar, where you cannot overinterpret the velocity changes for the much deeper depths. And we know that our measurement is actually on coda part that has a combined depth sensitivity of both bark waves and surface waves. It has been proved by Albert et al. In 2013 and 14. We just do the inversion based on the Rayleigh wave, and we also test the inversion based on log waves and bark waves. First, with log waves, the sensitivity kernels are very different from Rayleigh waves because they have shallower sensitivities and concentrate to less than 20 kilometers at depth. And we get the inversion result of velocity changes up to 50 kilometers at depth. In global, the velocity show the same features as last inversion, but the depth is much shallower. And we know that it's combined sensitivity from both surface wave and bark waves, so we also calculate bark sensitivities based on 3D radiative transfer equation. We test different couples of parameters with different mean free paths and different lapse time that we use to measure the phase shift. And we get these sensitivity kernels that has deeper sensitivity at depth than both different types of surface wave. This means that using the surface wave inversion, we actually underestimate the depth of velocity changes. The velocity changes should happen much deeper than using just surface wave. And the delayed effect may be somehow coming from lower crust, like the viscoelastic response, viscoelastic effect after the seismic, and also maybe some fluid transfer through the crust from due to the extension after the earthquake. So the physical interpretation of the delayed effect at depth is still ongoing, and we expect to have some result in the following months. And these are all depth-dependent Tohoku earthquake-related geology in Honshu, and we try to redo the inversion. We get all the spatial comparison and temporal evolution for quite large error, and we want to have more spatial information. So we redo the inversion for all different stations in this error, and we get the velocity changes in different layers changes with time. This is the very beginning for the monitoring, and we get this monitoring with temporal resolution of 30 days from 2011 to 2012. We can see the changes mainly happened within 30 kilometers. And in shallow layers, the most affected area is around here. And in deeper depths, it's moved northward and it's recovered faster for deeper part. And all of them remains negative till the end of our observation. Actually, the precise 4D monitoring needs precise 3D sensitivity code-wave kernels. This is the most important mission that we need to solve maybe in the next steps. But this very basic 4D monitoring can give us a very quick information that how velocity changes with depth and with time.
Why the maximum velocity change location shift at different depth?
This implies that for different depths, the physical reason that govern these velocity changes are different. So in shallow layers, it could be related to the damage, like the PG wave map shows the similarity. But for deeper depths, it compared with static stress changes. So the physical reasons that govern the velocity changes are very different regarding different depths. And to answer the questions about the spatial resolution of CUDA waves, as we calculate the cross correlation for less than 100 kilometers, so the spatial resolution must be larger than 100 kilometers. So that's why we need a very precise 3D CUDA sensitivities to do the 3D inversion to have a higher spatial resolution. But it's need some studies first to solve this CUDA sensitivity kernels. And okay, this movie brings me to the end of the talk. To sum up, I return quickly to the first part, the seasonal crustal seismic velocity changes throughout Japan. We first time showed the large-scale monitoring, and the seasonal effect could be related to different environmental factors like pore pressure changes, snow depth, and sea level changes induced loading effect. And the comparison with different geodetic observations should complement each other to have more information about the deformation of the crust. And the depth-dependent co- and post-seismic velocity changes related to Tohoku Oki earthquake show the depth-dependent geology that for shallow depths it could be easily explained by the nonlinear elasticity, nonlinear elastic effect, and for deeper past, it could be some effect from a lower crust, like a viscoelastic effect and some fluid transfer after the earthquake due to the extension of the crust. And the physical interpretation of this delayed effect is still ongoing. And for a more precise 4D monitoring, we need first to have a more precise 3D CUDA sensitivity kernels. Thank you for your attention.
Thank you, Qingyu, for the very informative talk. So we have time for like 2 quick questions. So anyone have questions?
Yes.
I have one quick
Yes.
question. So, are you expecting like an isotropic, azimuth anisotropic effect? Because the correct distribution of pore pressure related effects they're aligned in a prepared orientation.
The orientation of pore pressure effect. Is that?
I mean, yeah, for the
Oh, okay.
variation of your velocity variation.
Oh, yes. Yes, that's why we are separate actually different regions to see the post-seismic delayed effect to see if it could be related to
Direction.
yes.
The direction? Right now, you're
I don't see.
I don't see
The direction.
You are averaging all.
Yes,
all
yes.
You're averaging all directions.
Yes.
I see. So
And
you
if
don't
you
get-
yes.
look at
There's no unassigned.
For each station, it's averaged over all the surrounding stations within 100 kilometers.
And if you look at different
Direction.
Yes, we need to go to the pairs to see different,
Yeah.
but I have no more information about this right now.
One more question. Okay, let's thank our speaker and
Thank you.